Okay, good evening, Professor David Okay, it's September 27, 2023. The time is around 2 a.m. Okay, my topic for this session will be a continuation of our subject matter, AC machines, and I am now, and we are now on lesson number 23. Okay, let's proceed with AC machines, lesson number 23. The title of the topic for this morning will be AC Machines, lesson number 23, and the topic is example efficiency calculations, meaning we will be solving a problem that involves efficiency calculations for transformers. The last time around, I derived the formula on how to compute the efficiency of a transformer. Efficiency is actually power output over power output plus the total losses, and the total losses comprises the copper loss and the core loss. Okay, let's proceed. The following information is given by in connection with the test performed on a 50 kVA 4600/230 60 cycle transformer. The open circuit test values are actually E with the subscript is C, meaning the short circuit voltage is 230 volts. POC, meaning capital letter P with the subscript OC, meaning open circuit power is equal to 250 watts. This is actually the reading of the watt meter connected on the secondary side, okay, as the input for the secondary test, the reading of the watt meter actually is 250 watts, 285 watts, and the important thing about this is actually the core loss. This is the core loss. It is the loss on the transformer due to the laminations. Okay. For the short circuit test, capital letter E with the subscript is C, meaning short circuit voltage is 150 volts. And capital letter I with the subscript is C, meaning the short circuit current when performing the short circuit test. The short circuit current is 10.87 amperes. Capital letter P with the subscript is C. This is 615 watts. Okay, and this is actually the reading of the watt meter connected on the primary side during the performance of the short circuit test. And actually, this is the copper loss. Copper loss is termed to as the loss due to the resistance of the windings of the transformer, because there is no such thing as a perfect winding. Okay. Calculate the percent efficiency when the transformer is delivering rated kVA at a power factor of 0.84. Okay. To solve this problem, we just recall the formula on how to compute for the efficiency. That is, efficiency is actually power output over power output plus the core loss plus the copper loss. This is core, this is copper loss, right? This is multiplied by 100%. So if we could identify the power output, okay, and we could identify the core loss, okay, plus the copper loss, we could compute for the efficiency. Okay, I think the core loss is now given because the wattmeter reading during the open circuit test is actually the core loss. The core loss is actually 285, right? So if you do not know the open circuit test parameters, you could not identify the core loss, okay? The reading of the wattmeter during the open circuit test represents the core loss. So this is 285. And for the copper loss, the losses due to the windings or resistance of the windings, if we try to bring out the concept of short circuit test, the parameters that can be measured during the performance of this test is actually, if we try to consider the wattmeter, the reading of the wattmeter during the short circuit test is actually the copper loss. And what is given is 615 watts. Right? So if we try to take this sum, this is watts, this watts, so the summation will be watts, and this is 900 watts. So the total losses of the given transformer is 900 watts. And this represents the copper loss plus the core loss. How could we compute for the power output of the transformer? How could we compute? Power output is actually kVA subscript load times power factor times 1000. It is like this. Power factor, one of the formulas for power factor is actually true power over apparent power. And this apparent power is actually represented in kVA. So if the apparent power S is in kVA, supposed to be this is in kilowatts. Okay, so this is K, this K, it's fine. They are of the same nature, right? Kilowatt over kVA. So if the true power is watts, they should only be volt ampere. Okay, so you could divide a kilowatt over kVA or simply watt over VA. But in here, we are computing big apparent power because the given apparent power is actually kVA. So if we try to compute for P, the true power is actually kVA times power factor, right? And to convert it to simply watts, we multiply this by 1000 watts per kilowatt, right? So this cancels. This K here cancels, right? So if we try to multiply the given kV by 1000, it is now watts if we try to multiply it by power factor. So I place it in the computation. Capital letter P with the subscript output, meaning output power in terms of true power. It is actually the given kVA load times the power factor times 1000. Okay. The rating 50 kVA is actually the output of the transformer. So that will be 50 kVA multiplied by 0.84 times 1000. If we try to multiply this one, this should be 42,000 watts. Okay. So meaning to say the power output, if the given load is 50 kVA and the power factor is 0.84, it's only 42,000. So, and the total power input now will be the total power input is actually the bottom portion, right? So it will be the power output plus the total losses. So this should be 42,000 plus 900, and the total power input should be equal to 42,900 watts. And what's the significance of this one? Meaning to say, the total input power should be 42,900. So when we subtract the losses, it will come out as 42,000 watts. Just to produce 42,000 as output, we must have to produce 42,900 watts. Okay, so if we try to compute for the efficiency is power output over power input. power output is 42,000. Power input is actually the power output plus total losses, which is 42,900. So this is 42,900 times 100%. So the efficiency now with the subscript FL, meaning at full load, is 97.9%. This is very high. Like what I said in the annotations on the study of the concepts of transformer operation, transformers has high efficiency. It's more than 95%. So we have computed to be 97.9%. So this is correct. Okay, that's it, guys. That's the way how to compute the efficiency of a transformer, right? And in the computation of the efficiency, we must have to identify the total losses. The total losses actually represents the copper loss plus the core loss. Okay, this copper loss emanates from the short circuit test. It's the reading of the wattmeter during the performance of the short circuit test. And the core loss, it is actually the watt reading of the wattmeter during the performance of the open circuit test. And this is actually 285 watts for this given transformer. Okay. Good morning from Los Angeles. This is Professor David J. DelosReyes.